Buenas tardes a todos.
Good evening, welcome.
Es un placer
It's a great pleasure.
ver
It's
la
an
sala
honor
llena.
to see you
tan
very
hermoso
many of you at a beautiful day
Vamos
like
a
today's,
tener la
but
ocasión
we'll have the unique
de
occasion
escuchar a
of
uno de los
enjoying a wonderful
mejores
lecture
investigadores
by
que
one of the
tiene Reino
best
Unido.
researchers
De
from the
hecho,
United
como
Kingdom.
veréis,
As
lo
you will
que os voy a
see,
describir
what I'm going to
es reconocida internacionalmente
mention
y además ha sido
is
galardonada con varios premios y varios reconocimientos por parte de la
so that the
Unión
lady's
Europea.
got many awards from
La
the
profesora
European Union.
Catherine
Professor
Heymans
Catherine
es
Heymans
catedrática de
is
cosmología observacional,
professor of
título
observational
específico,
cosmology,
cosmología
that specific
observacional,
name,
de la Universidad de
observational
Edimburgo,
cosmology,
en
from
Escocia.
Edinburgh
Ha
University,
trabajado en Oxford,
Scotland.
en el Max Planck
She's
Institute
worked at the Max
en
Planck
Alemania,
Institute
Cita, en Canadá,
in Germany, Oxford,
y ha disfrutado de
Canada,
prestigiosas
and
becas
she won
Marie
very
Curie,
important fellowships at
etcétera,
Max Planck Institute of
de la
Astronomy,
Unión
British
Europea.
Columbia
De
Institute of
hecho,
Astronomy
gran
from
parte
Paris,
de
University of
su
Edinburgh, and
investigación está
part of her
subvencionada
research
por la Unión Europea.
is thanks to a grant from the European
Como estaba
Research
ya en
Council.
ocasión, esto, sin duda,
As you know,
pues, plantea ahora serios problemas con el
now
Brexit.
there is a problem with
Esto no le
Brexit,
impide a ella
but she
seguir
will
adelante con su
continue
investigación, naturalmente.
on with her research project, I'm
Es
sure.
autora de más
She is
de
the author
100
of more than
papers,
100
artículos
papers
en revistas de alto impacto.
at the most prestigious
Pero quizá lo más
journals.
relevante
But the most
es,
important thing is
su liderazgo
that
en
she has a capacity of
fotografiados
leadership,
como el,
mapping, for
Kilo Degree
instance,
Survey, o KITS,
the Kilo Degree Survey,
del
KITS,
Observatorio Europeo
from the
Austral en Chile,
European Austral Observatory
CFHTLS,
in Chile, and the
Canadian
CFTLS, the
French-Hawaiian
Canadian-French Hawaiian telescope,
en
that
Hawái,
survey
uno de los
based in
telescopios de
Hawaii,
Hawái.
one of the telescopes
Además,
based in
autora
Hawaii.
de
She's
un
the
libro,
author of
The
a
Dark
book,
Universe,
The Dark
de
Universe,
lo que nos va a hablar,
and she's going to talk about that,
del universo, que ha sido publicado
viewing
muy
the dark
recientemente, en febrero
side
de
of the
este año.
universe. She published her book last February,
Además, ha recibido, como
and
mencionaba,
she's
diversos premios,
received many
de los
awards,
cuales cabe destacar
among
dos,
which I'd like to point
que han sido
out
muy interesantes.
something
Chancellor's
that's very important.
Rising Star
Chancellor's
Award de hace 2 años, 2015,
Star Award
y el
from
premio
2015,
George
and
Darwin.
George Darwin.
George,
George,
Charles, es el
it's
hijo.
not Charles,
Charles,
it's
el
George
biólogo.
Darwin. It's the biologist.
un astrónomo
Charles is a biologist, but
reconocido,
Charles is an
y es un
astronomer
premio
very
que concede la Royal
well known,
Astronomical Society.
and that's an award given by the Royal Astronomical Society from the UK, and she got this award. Congratulations, you've got the 2017
Además,
award.
Catherine es conocida
And
por su
Catherine is well known.
divulgación
She's a
y
wonderful
me gusta que
lecturer,
vais a disfrutar.
and I know you're going to enjoy today with a unique opportunity, a wonderful
Tras la
lecture.
divulgación que ha dado en
And
diversos
she's
países,
presented
quizá
the
los más
subject at
llamativos
very
son
many
en Estados
countries,
Unidos, en Aspen,
United States,
y en
Aspen,
Londres, en la
London,
Tate Gallery,
at the Tate Gallery, the
Es
modern
además
gallery.
consultora
And
científica
she's also a consultant
del
and
pabellón del
advisor
Reino Unido en la Exposición
of
Universal
the
2017,
2017
tendrá lugar dentro de 33
Expo
días.
that will
Si
take
alguno
place
quiere
within
sacar su
33
billete
days. If you want to buy a ticket to go
bastante
to
exótico,
a
Astana,
very
en
exotic
Kazajstán.
place, Kazakhstan,
Sin más,
go to Astana,
preámbulo,
to
le doy la
2017
palabra a la
Expo.
profesora Catherine Heymans.
And Professor Catherine Heymans, you have the floor. Welcome.
Thank you very much. Now, I'm told that I was only 6 years old when I asked my class teacher, what is the most exciting and challenging job in the world? And she hesitated a little, and eventually she said, I don't know, a brain surgeon or an astrophysicist? And it took me till about the age of 17 to decide which of these two paths I was going to take. And I set off to the University of Edinburgh in Scotland to become an astrophysicist. And I took my degree there. Now, I was coming to the end of my degree, and I went to see my course professor. And I said to him, what's the most exciting and challenging problem in science right now? And this time there was no hesitation. He looked me straight in the eye, and he said, Catherine, find out why the expansion of our universe is accelerating. Wait a minute. Now at that point in my career, I knew that our universe had started with a Big Bang, and the energy from that Big Bang was causing our universe to expand. But I I'd kind of always felt that that energy would kind of run out at some point, gravity would win over, and our universe would come back in a beautiful apocalyptic crunch, and there'd be a rebirth of a new universe. And I kind of liked that theory. But what my professor was telling me at this time in my career was that there had been brand new measurements that were showing that not only was the universe expanding, but that expansion was getting faster and faster each and every day. It was as if there was this new source of energy that was gaining momentum, causing this very rapid expansion. Nobody knew what it was, nobody knew where it came from. And he set me that challenge to try and find out what it was. I like a challenge, so off I went to Oxford to study my PhD, and we can fast forward now 15 years to the present day, and I don't have the answer yet. We know a lot more, though, than what we knew 15 years ago. You might be surprised to learn that the stuff that you and I, and the Earth, and the Moon, and the Sun, and everything that we can see in the universe, all of that stuff that we can see makes up less than 5% of our universe. The rest of our universe is dark. You can't see it, you can't touch it, but we know that it's there because of the effect on the things that we can see. Now, there are two entities on the dark side. We've got something that we call dark matter. Now, dark matter is a strong gravitational force in our universe. The other entity we call dark energy. This is that mysterious source of dark energy that I was set on a challenge to find that's causing this accelerated expansion. Now, if we look at our understanding of fundamental physics today, that can explain many of the things that we see around us, that can explain the particles that we're made up of, that fundamental knowledge of physics cannot explain dark matter, and it cannot explain dark energy. So basically, we don't understand 95% of our universe. 95% of our universe we can't explain. Now, you might like to think of that as a failing as us as scientists, but how I like to view it is an amazing opportunity. Because when you don't understand something as massive as 95% in the universe, it's clear that you're missing an important piece of the puzzle. Now, it's very widely believed that our final understanding of the dark universe is going to have to involve some sort of new physics. And that's why this area of research is so exciting. And what I want to share with you this evening is different theories that we have that might explain the dark matter and the dark energy in our universe, and the different observations that we're going to make to challenge those theories, to confront those theories. Now, I'm going to start off with just getting an idea of scale, because tonight we're going to be talking about the universe on the absolute largest of scales. So let's build up. We're on planet Earth, which is just one planet. And our sun is just one star in over 300 billion stars in our own Milky Way galaxy. Okay, so we're up to our scales in our galaxy. We're going to pause there in our journey of scale in the universe, and I'm going to give you a first key piece of evidence that supports the theory of dark matter. And to do this, we're going to do a little bit of a thought experiment, which requires my prop here. So, now I'm sure you've all done this at some point in your life. If you spin a ball on a piece of string around your head, if you want to spin that ball faster, you have to hold on tighter to the string. If I hadn't have held on tighter, that would have flown out into the audience. Okay, has everyone had that experience in their life? Yeah, you've got to hold on tighter. Okay, what on earth has that got to do with dark matter? Well, let's take a look at a galaxy. Now, a galaxy is full of billions of stars, and those stars are orbiting around in the galaxy. And this galaxy isn't too dissimilar from our own Milky Way galaxy. Okay, so imagine the knot at the end of my scarf is a star, and it's spinning round and round and round in the galaxy. Now, the stars that are moving around in the galaxy, they're not stuck on by a piece of string. No, it's gravity that holds the galaxy together. Now, the more stuff you have, the more gravity you have, okay? And you can go and count roughly how many stars there are in a galaxy. We know roughly how much a star weighs, so you can work out how much mass, how much stuff there is in the galaxy. And then you can measure how fast those stars are moving around, sort of like how fast the scarf was moving around my head. And the sums just don't add up. If you just look at just the mass that we can see in the galaxy, there's just not enough there, not enough gravity to keep those stars going round and round and round. If there was only the mass in the galaxies that we can see, then the stars would simply fly off into the universe, just as my scarf would have flown out into the audience if I hadn't held on tight enough. And these observations allow us to draw the conclusion that there must be a massive halo of dark matter, stuff that we can't see, that's there providing that extra gravity to keep all of those stars orbiting round and round and not flying out into the universe. Now, at this point in the evening, I'd just like to take a little poll of my audience here, just to see how you're feeling. I've just asked you to believe in a dark matter particle that you can't see or touch, and I just want to get a sense of how you're feeling this evening. So I've got a question for you. What do you think this mysterious dark matter that I've just told you we need, if we don't have it, the stars would simply fly out, what do you think it is? Okay, you've got 3 options to choose from here. Option A, dead or weakling stars that we can't see. So I said we're looking for stars. Maybe there are just some other stars there that are just really faint we can't see. Could it be that there's a new type of particle that hardly interacts with the stuff that we're made up of? That's option B. Or C, a tooth fairy that astronomers have made up because they've got their sun wrong. Do you have tooth fairies here in Spain? In Britain, it's like if you lose a tooth, you put your tooth under the pillow. Yeah, it's like an imaginary thing. Okay, good. Right. You can only vote for one choice, and I am up front and I can see you all. Okay, good. All right, who would like to vote for number 1, number A, that the mysterious dark matter is just some dead weakling stars that we haven't managed to see? Gentleman over there, thank you for being brave. Gentleman back there, thank you. A few over there, a smattering in the audience. Okay, a new type of particle that hardly interacts with the stuff that we're made up of, and that's why we haven't detected it yet. Oh, that's a sizable number in the audience. And option C, it's a tooth fairy that I've made up because I've done my sums wrong. Oh, we've got double hands over here. Thank you, sir. Excellent, excellent. Okay, so the majority of people in the room agree with the common consensus in the scientific community that there is a new type of particle out there that hardly interacts with the stuff that we're made up of, and that's why we haven't detected it yet. But there is a sizable number of you who think the other options. Let me tell you a little bit about option A. This was actually one of the first research projects that I worked on to go and look to see if there were any stars that we weren't seeing. There's been a lot of work done on this using lots of different techniques, and we're really fairly certain that that isn't the answer. In fact, we are certain that isn't the answer. There are certainly some dead weakling stars out there, little brown dwarfs, but not enough to account for the missing matter. And option C, people who voted for option C, I sincerely applaud you. As scientists, we have to question. We shouldn't take everything for granted. We should always ask to see the evidence and the research behind it. And I applaud your scientific argument there. But for the rest of the talk this evening, we're going to assume the hypothesis that there is a new type of particle out there that we haven't seen before. That's what we're going to assume. We're now going to continue on our tour through the universe, given that our own Milky Way galaxy has got this large halo of dark matter around it. Now, our Milky Way galaxy is just one galaxy in our local group of galaxies. And if you look up on a really dark night, you should be able to see Andromeda with the naked eye. That's our closest neighbor. And often you find also that galaxies can live in massive clusters of galaxies, where you see thousands of galaxies all together. And we're going up on scales. And what we find is that if you look at these galaxies on an even larger scale, they are forming a giant cosmic web. Now, what I'm going to show you now is a movie that comes from the Sloan Digital Sky Survey. And this is a fly through their data. Each of the little blobs that you see going past is an image of a galaxy that it's taken, and they've positioned them at the right point in space. This is real data. This isn't a made-up movie game. And what I want you to take away from this is the galaxies are not randomly distributed. Okay? If you look at where the galaxies lie, you see that they're kind of forming this kind of webby-like structure in the universe. Now, what you can see here now, this is a computer simulation. And this is what we think the universe would look like with certain models of what the dark matter particle is. So that model that the dark matter particle is weakly interacting, option B in our vote. Now, if you do a computer simulation of how the universe should evolve and grow with that type of dark matter particle, this is what you would see if you could see the invisible dark matter in our universe, this webby structure. And I've just put the galaxy movie, that's real data at the top and a simulation at the bottom there. And so we have this hypothesis that it's the dark matter in the universe that dictates where and when the galaxies form, and that's why we see the galaxies in this web-like structure, but they're there because it's the gravity of the dark matter that's seeding them there. If you like, you can imagine the dark matter as kind of like a cosmic scaffolding upon which the luminous universe that we can see is built. Okay, just pause this for a bit. Now, this is great. We've got a good hypothesis about our dark matter. If we look at where the galaxies are, they appear to follow this cosmic web, which is what we'd expect from dark matter. But I want to actually observe dark matter. I know I can't see it, I can't touch it, but I really, really, really want to see this invisible dark matter. So how are we going to do this? So what I'm going to do now is show you a little video from my friend Phil Marshall. And you can do this experiment whenever you're next at home having a candlelit dinner. Okay, so what he's going to do is he's going to look at a candle through the base of his wine glass. Now what you can see when he looks through the base of the wine glass is he sees more than one candle. And that's because the light from that candle is traveling through the base of the wine glass and it gets bent and distorted. Okay, so this is, for those of you who are wearing glasses in the audience, your glasses are doing the same thing. They're slightly bending the light so you can see me. Now this effect is called lensing. And what it means for our eye, when we see it, is we perceive there to be several objects. Now this same physical effect occurs in the universe, but now we don't have massive wine glasses out there. Now instead we have big clumps of dark matter that is curving space and time that changes the path of light as it travels through the universe. I've got another movie of that here. Here we've got light from a distant galaxy that's traveling towards us on Earth, and it's going past a big clump of matter. Now that clump of matter is so dense, so strong, that it's curving the entirety of space and time. So as that light travels towards us, it gets bent and distorted, just like the candlelight got bent and distorted as it went through the base of the wine glass. Now we can use this effect to tell us how much matter there is out there. And it doesn't matter whether it's dark matter or luminous matter, it simply doesn't matter. And what we can do, here's another diagram just to show, is we look at galaxies in a very, very distant universe. Their light travels across the universe towards us. And each time it goes past a dense clump of dark matter, it gets bent and distorted. So when we look at those images of the galaxies on the sky, what we see is a very, very weak alignment between them. That distortion just makes them appear to say, very slightly line up with each other. So if you like, you can think of this as kind of like a message that dark matter leaves for us on the sky. It's kind of imprinting the fact that it's there by just distorting the images of the galaxies behind it. Now, the project that I'm working on at the moment is a large European project called the Kilodegree Survey. And you can see the telescope here. It's the VST telescope. And it's on top of one of the best observing sites in the world in Paranal in Chile. And what's great about this telescope is whenever the weather is perfect, it looks at our patches of sky to map out the galaxies. This is one example observation that we made. You can see lots of blobs there. And in the middle, there are really a lot of galaxies. It's a massive cluster of galaxies. So we go and we look at all of the galaxies, and what we're looking for is that very weak alignment that's caused by this dark matter, this lensing effect, and we can use that to tell us where the dark matter is. And I'll show you that in pink now. because dark matter is pink, I've decided. And you can see around where there's this massive clump of galaxies, there is a massive clump of dark matter. Now, this is a tiny, tiny patch of sky. So let's have now look at the dark matter across the entire patch of sky that we've observed. Now, at the top, this is a real map of dark matter that we've made. And just to give you an idea of scale, if you imagine looking up at the night sky and put your arm out at length, this strip across the sky is about the size from your elbow to your wrist. It's about that patch of sky. So quite a sizable patch of sky. And the blobs you can see there, the brighter the blob is, the more dark matter there is there. And as the colour scale gets darker, then there's less to no dark matter. Now, at the bottom, I've given you a picture of the computer simulation, and it's kind of like the real map of dark matter that we've made is just kind of like a blurry, low-resolution version, but we're getting there. But you can see the same sort of effects. You have blobs where there's lots of dark matter and dark regions where there's no dark matter. And what we found with this sort of data is exactly what we'd expect, that the dark matter that we can't see is mapping out where the visible, the luminous stuff that we can see in our universe lives. The dark matter is housing those galaxies. Okay, so I was wondering this evening whether you might like to partake in a little science experiment with me. Because those of you who are astute in the audience will probably be thinking this through. Catherine has told us that there's lots of dark matter surrounding our own Milky Way galaxy, because if there wasn't, then the stars would fly out. She's also told us that there's this magic cosmic web of dark matter everywhere that sort of decides where the galaxies we can see are, and she's shown us a real map of dark matter that she's made with this awesome telescope. This must mean that there's dark matter in this very room, because I've told you it's everywhere. So I was wondering this evening whether anyone wanted to see if we could try and catch a dark matter particle. Are we game? Yes? Okay. So to do this, you're going to need to form a little dark matter butterfly net. So if you'll indulge me by just putting your thumb and forefinger together like this. Yes, thank you. Excellent, excellent. Good. And what we're going to do is we're going to count to 5 together and just see if we can catch any dark matter particles in those 5 seconds, okay? Just entertain me with this. I've got small children at home. We do these sort of games. Okay, and we're going to count to 5. Oh, let's see if we can do it in Spanish. 1, 2, 3. Oh, I've forgotten 4. 4, 5. Excellent. Now, keep your dark matter butterfly net up if you've caught any dark matter. Does anyone feel like, oh, lots of people feel like they've caught some dark matter. Excellent. Excellent, congratulations, Nobel Prize for the lady in the 3rd row who's caught some dark matter. This is fantastic. Our theories of dark matter aren't well known, but in those 5 seconds, between 1 million and 1 billion dark matter particles have flown through your dark matter butterfly net. Well, they've flown straight through. Now, in the time that it's taken you to come here to the foundation this evening, to sit down, to listen to our talk, and probably also get home, in that time, there will only be one direct collision between a dark matter particle and the particle in your body. Okay, so there are millions and billions of them flying through this room, but they're so tiny relative to the particles that are in our body, they just don't see the stuff that we're made up of. They don't interact with the stuff that we're made up of. But it's absolutely everywhere. Now, people are trying to catch these dark matter particles, and they have bigger dark matter butterfly nets than our dark matter butterfly nets. Deep underground mines. I'm sure you're all James Bond fans. I always think of this as kind of like a Dr. Evil's lair, deep underground. And the reason why they go deep underground is that shields you from lots of other particles that are flying through us at the same time. This is just one example. There are lots of different detectors out there. This is the Lux Zeppelin dark matter detector. 10 tons of xenon buried deep under the South Dakota mountains. And the idea here is that this is a giant dark matter butterfly net. The dark matter particles are flying through. One of them, or 2 of them, or several of them will knock into these xenon particles. That will give a little bit of energy to the system, and that can be detected in these scintillator tubes. They haven't found anything yet, but we're hopeful that soon they will. I mean, this is amazing new technology that they're really building on, and the hope is that they will discover evidence of these dark matter particles. We also have our friends at CERN, at the Large Hadron Collider, and the hope there is that they will actually create some dark matter particles in their collisions. I feel like in the next 5 years, we should have a discovery of the dark matter particle. Science is really moving in that direction. If we don't, then we can go back to option C in our poll earlier, that it's just something that we've made up. But soon, I really feel that we'll make a breakthrough in this field. So that's one of the dark entities, hopefully covered. Hopefully you'll believe that there's something out there called dark matter. Dark matter only makes up 25% of our universe. So we've got 5% of the universe is made up of the stuff we're made up of, 25% dark matter. The rest, dark energy. Our best theories about dark energy need me to tell you a little bit about the physics of nothingness. Now, there are big regions of our universe where there is absolutely nothing. No gas, no particles, no dark matter, nothing. A complete vacuum. Nothing at all. Except teeny tiny virtual particles that can pop into existence and back out again. Now, when a particle pops into existence, it can give energy to the system. And this is not just me making something up. This has actually been measured in laboratories. It's a prediction from quantum physics that this phenomenon can exist, and it's been measured. And it kind of acts a bit like a perpetual motion machine. So if you have an empty space, these virtual particles can pop into existence. They can give energy to the system, which fuels the expansion of the universe, which creates more empty regions of space, which creates more opportunities for virtual particles. And so you can see this dark energy, this vacuum energy, can gain momentum, fueling this accelerated expansion of the universe. And it is a beautiful, beautiful theory. And maybe we'd say, okay, we're done. We understand it. But there is a bit of a problem. Measurements of distant supernovae can give us a really good estimate of exactly how much dark energy we think there should be. And quantum and particle physicists can also tell you how much they think there should be based on their theories and their measurements in the lab. Now, it's quite often that particle physicists and astronomers disagree with each other. That happens quite often. But this time it's a really big monumental disagreement because the numbers differ by 10 to the power 60. So that's 1 with 60 zeros after it. That's how much we disagree in how much dark energy, between how much is measured and how much we think. So I think it's time for another poll of our audience this evening, just to see, which side of the argument you guys are on. So I'd like you to think about this idea of this vacuum energy. It's a beautiful theory that can explain this mysterious dark energy, but we've got this disagreement between the particle physicists and the astronomers. So I'd like you to think about who's got it right. Is it the particle quantum physicists? Have they done their sums right? And the astronomers have just made their measurements wrong? Maybe the supernova astronomers who have made their measurements haven't got it quite right? Or none of them have got it right? Okay, and again, you can only vote for one. Voting for who thinks the particle physicists have got everything right. Excellent, excellent. Excellent. Who think the astronomers have got things right, and it's just that particle physics theory isn't quite on a couple of, yes, thank you, yeah. Oh, less for the astronomers than the particle, okay, good. And neither of them got it right. Yes! Very good, a skeptical audience. I thoroughly approve. I can tell you for certain that the particle physicists cannot have got it right. If their estimates are right, our universe would not exist, because the energy that they predict would be given from this effect. Simply, the universe would have expanded at such a rapid rate that stars and galaxies wouldn't form and we wouldn't be here. So I know for sure that they have got it wrong, or they're missing a piece in their puzzle. It could well be that the astronomers have got their measurements wrong. And this is critically important. I said at the start, the reason why we're interested in the dark universe is because we believe that in order to understand it, it's going to have to involve a breakthrough in physics, something really different. And you're not going to believe it if it's just one measurement tells you that that's the right answer. We need lots and lots of different experiments, different observations that test these theories from all different angles, so we get a really clear answer on what could be causing this mysterious dark energy in the universe. So, yes, is this one tooth fairy too far? I think the audience vote said yes there. What I'm showing you here are two simulations now. On the right-hand side, we have a simulation of a universe with just dark matter on its own. And the number that you can see ticking down on the clock is just time to the present day. And I want you to compare the two. On the left-hand side, you've got a universe where you've got dark matter and dark energy. Now, I kind of like to think of dark matter and dark energy as kind of like fighting twin siblings, okay? So you've got dark matter, which on its own would manage to pull all these structures in the universe together. Gravity likes to pull things together. But when dark energy comes along, it makes that job really hard because it's causing the expansion of the universe to grow. So the distances between objects are changing, which makes it ever harder for dark matter to pull these structures together. I kind of think about, well, I'm always thinking about my children at home, but I kind of think that one of them's making like a nice jigsaw, dark matter's kind of putting everything together, and dark energy just comes in and just throws the whole pieces out. Now, these warring factions on the dark side, we can actually use that interaction between the two of them to test different theories of dark matter and dark energy. Now let's just recap. I was telling you about this really cool technique that we can use called lensing, whereby the light from distant galaxies gets bent and distorted by all of the dark matter in between me and those distant galaxies. And that allows me to map out the dark matter. But I can do that at lots of different epochs in the history of the universe. If I want to look back if I want to go back in time and see the universe as it was a long time ago, all I have to do is look further back into the universe. And so I can make these lensing measurements at lots of different times in the epochs of the history, and I can see how dark matter structures are growing and changing with time. And that gives me a really unique way to test what dark energy is actually doing, how it's making dark matter's life really difficult. Now I'm only going to show you one really research plot this evening. We published this early this year. This comes from the kilodegree survey, that telescope I showed you earlier. And what we're looking for with this lensing technique is the galaxies, we want them to just line up with each other. Let's just zip back to this picture. So as the light goes through the dark matter, it gets bent and distorted, and they kind of line up with each other. Now this plot shows you how aligned the galaxy pairs are on the vertical axis versus their separation. So if I have two galaxies, let's do it this way. If I have two galaxies that are close to each other on the sky, their light, as it travels towards you, the observer, gets bent and distorted in the same way, okay? So they end up looking like they're lined up with each other. But if I have galaxies that are separated far on the sky, which would be this side of the plot, they're really far separated, then their light will travel through different structures of dark matter, and they won't line up with each other. Now, and you can see that in our measurements. So on small scales, they line up with each other, and as you go to large scales, they don't line up with each other. Now, the different lines that you can see there are different models for how the dark matter should be behaving. The more dark matter we have, and the clumpier it is, the stronger the lensing signal that we predict. Now we've made this measurement. This is a cartoon here of how the universe is expanding, and we've made this measurements at lots of different times in the history of the universe. So we know how dark matter is clumping at lots of different times. And remember, what dark energy does is it slows down those dark matter structures growing. So it makes it harder for them to clump. Now, what we found is not what we expected. I said if we're going to test these theories of dark matter and dark energy, we need lots and lots of different ways to look at it. And in astronomy, we have loads of different ways to probe the universe at different points in its history. And the most exquisite results come from something called the cosmic microwave background. These are images that have been taken of the universe right after the Big Bang, to when dark energy hardly existed. These are exquisite measurements. It's these measurements that have told us exactly how much dark matter and dark energy there is. But we can use these measurements at the Big Bang to predict what we think the universe should look like today with our models of dark matter and dark energy. And unfortunately, they just don't meet up. There's a kind of a dividing line. There are different ways that we can measure the universe at different times, and they simply don't agree. There's this inconsistency between the different ways that we're measuring things. Now, there are different opinions you can take on this. You can go back to our first polls that the astronomers haven't got things quite right. But we've been working on this for a long time now, and I feel very strongly that we've done a really good job. And of course, we need more data. We need to do more experiments to be really sure. But what it's looking like at the moment, when we look at the dark matter using this lensing technique, it's much smoother than we'd expect. And that would suggest that dark energy is doing something really funny in the present-day universe. And that's giving us maybe another clue of what this dark energy is. Okay, I'm now going to tell you about the zoo of different dark energy models that are out there, because the theorists are having so much fun with this. They're coming up with some great new theories. Now, I've already told you about this idea that it could be coming from the vacuum, and it's a beautiful theory. It has this problem that the numbers don't quite add up, and also, if this was the right theory, then also we wouldn't have this disagreement between these different probes. So, best guess, but we need to go further than this. Another idea is perhaps there's some new energy field out there. There are 4 fundamental forces that we know about. Maybe there's a 5th one. Maybe there's something that we haven't thought about before, some new energy field that's giving this new period of inflation to our universe. These are fun ideas. You know that there are 4 dimensions. You've got 3 dimensions of space, 1 dimension of time. That's how we live. Perhaps there's a 5th one out there that's somehow interacting with the 4 dimensions we live in. Perhaps these dimensions are colliding with each other, causing this accelerated expansion. Perhaps our universe is just one universe in a sea of different universes, and we just happen to be in a weird one. That's a multiverse theory. Now, what my team has been working on is questioning gravity itself. And I know this is rather radical, and I think if I'd tried doing this about 10 years ago, I probably wouldn't be a professor today, because they would have already thrown me out. But listen, we don't understand 95% of our universe, and that's a big thing. And when you've got such a big challenge like that, you have to question everything. And everything I've shown you so far today is built on our understanding of gravity that comes from Einstein's theory of general relativity. And I think we're coming to the point now where we actually really need to question that. Now, in our own solar system, on Earth, Einstein's theory of general relativity explains things perfectly. There is no better theory to explain how things work in our solar system. But we're in quite a unique region of space. You know, we're inside the Milky Way galaxy. Gravity's never been tested on the large scales of the universe. On the emptiest regions of the universe, who's to say gravity doesn't act differently there? Let me tell you a little bit more about this idea. So Newton, of course, was the first person to come up with his theory of gravity. And his theory went a bit like this. Stuff attracts stuff. Apple falls on head. But his idea was that gravity worked the same everywhere, that big G was a fundamental constant, it's the same in all space and all time. And then Einstein came along and said, no, it's not stuff attracts stuff. It's that gravity bends the entirety of space and time and things just roll together. But this is a fundamental constant that happens the same everywhere in space and time. So we're questioning this, and we're asking questions like, does gravity bend space and time differently? Now, we know in our own lives that space and time are quite different things. No matter how much you might want the last 45 minutes of your life back, it's gone. It's gone. So we know that space and time are different. Perhaps gravity bends space and time differently. This we need to test. Who says that gravity is really a constant everywhere? We need to test this. Now, I'm not saying that this is the right answer, but what I'm saying is that scientists, it's our job to question everything. When we don't understand a big problem, we have to go out and search for these things. Now, we've done some tests already with the survey that I showed you, the kilodegree survey, and we're not there yet. All of our data is consistent with Einstein's theory of general relativity, but it's also consistent with lots of other theories. So we need more data, better data, with which to really confront these different theories. So here is an image of some galaxies that are taken from Paranal, so the best observing site that we have on the ground. They're very small, distant galaxies, and you can see they're quite fuzzy. This is what they look like from space. I'll just do that again. Okay, so if you can launch a telescope above the atmosphere, you get a much keener vision, a much clearer vision of the universe. And if you're trying to measure this very weak lensing effect, I was saying dark matter makes things line up with each other. If you're trying to detect that, then going above the atmosphere to enable you to see that makes your life so much easier. In the next few years, we're going to see these two major new facilities coming online. Euclid, it's a 1.2 meter telescope in space. This is a major European project that Spain has a really critical role in. And it's going to be producing Hubble Space Telescope quality images across the entire night sky. This is going to be an amazing project that's going to allow us to really cleanly detect this signature that dark matter has left on the images of these distant galaxies. Now, on the same time, on the ground, we've got a project called LSST, the Large Survey Synoptic Telescope. Now, this is an 8.4 meter telescope. It's a massive, massive telescope. It's going to image the entire night sky every 3 nights to find killer asteroids that might one day obliterate planet Earth. Awesome. What we can do with those images is we can stack them together, and over 10 years we're going to build the deepest image of the universe that we've ever seen. Now, with this quantity of data, and with all of our different ways of questioning the dark universe, we'll be able to really confront these different theories, and then we'll be able to tell you what is causing this mysterious accelerated expansion. And my hope is that before I retire, I will have been able to answer the question that my professor set me 15 years ago to discover why our expanding universe is accelerating. I'm going to end... Oh, no, I'm not going to end there. Ha-ha. Do I have time for a final poll? I do. Excellent. I'm intrigued, after you've heard all of my discussions of our theories, I'm intrigued to learn what the citizens of Madrid think that these major new 2 facilities will discover. I've got 5 options here, because I thought I'd give you a lot. So do you think that the simplest explanation, that it's just this vacuum energy, is the right answer, and it's just the particle physicists have got their numbers wrong, and that's the right explanation? Do you think that we need to upgrade our theory of gravity, that maybe Einstein hasn't quite got it right? Option C, we've got it wrong, we've misunderstood our observations, and everything I've told you this evening is not quite right. Please don't go for that one. Option D, we're in a weird universe in a sea of universes, which is the final option, or E, other. Okay. Is everyone ready to vote? Okay, option A, the simplest explanation, dark energy is just coming from the vacuum and the particle physicists haven't quite got their sums right. A couple? Yeah, okay. Option B, Einstein hasn't quite got it right. We need a new theory of gravity. Excellent, excellent. You're not allowed to... Oh, good. Right, okay, yeah, a smattering for... Option C, astronomers have got it wrong and has misunderstood their observations. Option D, we're in a really weird universe, in a sea full of universes. Lots of multiverse fans in the audience. How exciting. We can talk about the multiverse in the question and answer session afterwards if you want to. And E, other. So I think it's a pretty even split between everything apart from option C, which thankfully nobody voted for. I did this poll with my undergraduate students in Edinburgh a little while ago, and one of my students voted for other, and I thought, fantastic. She's going to tell me the answer. She's going to have come up with a brand new solution. I said, what other thing do you think they'll find? And she said, well, you know, Catherine, given the state of things in America, I just don't think LSST will ever finish being built because it will lose all its funding, and quite frankly, Euclid's going to blow up on the launch pad. So that's the optimism and enthusiasm of my students today. No, it's just one of them. I hope that's not the case. I genuinely believe that we're going to make some major discoveries, and you'll see this field really rapidly advance over the next few decades. Things I want you to take home this evening to tell your friends. Key point number one, our own Milky Way galaxy has to have a halo of dark matter around it. If it didn't, then all of the stars would simply fly out into the universe. We need dark matter to keep our own galaxy together. Our entire universe is filled by a giant invisible cosmic web of dark matter that we can see if we use these amazing lensing techniques. I've told you there's a mysterious source of energy that we call dark energy that's speeding up the expansion of our universe, and we don't really know why. And the reason why you should care, and the reason why I'm delighted that so many of you are here this evening, is because this is really exciting new physics, because I genuinely believe our final understanding is going to have to involve some sort of new physics that will forever change our view of the world around us and the universe. If you are interested and you want to learn more about this, I have written a book. It's free. If you just Google my name and Dark Universe, you can find it. It's an Institute of Physics book that talks about a lot of the things that I've talked about this evening. And if you're interested in more than the Dark Universe, then we have an online course. Again, it's free for you to take, and it's a course. We've had almost 40,000 students take this course now, and it covers the science and technology behind astronomical discovery more than just cosmology. Thank you for your time this evening.